Thanks. I'm Yang, and very happy to give the talk on behalf of HuFu team. And HuFu is actually a Chinese word. It is totally in the shape of a tiger. It is used for authenticate in Asian China. And we use this name to, we use HuFu to name our signature schemes. That is hash and Psi lattice signatures. And it follows the gauge-based GPV framework. And its security as square root, it is also based on unstructured lattice assumptions. It is based on plain LWE and sys problem. And as Thomas just introduced before, typical hash and silence signatures use a good representation T called trapdoor of the lattice as the secret key, and the public key is a bad representation. And to send a message, it first maps the message to a random point M and use the trapdoor from a lattice point close to M. And for verification, it can use the public key to verify if the signature V is a lattice point and if it is sufficiently close to the hashed message. Early hash and Psi signatures were broken because their signature distribution is dependent of the secret key, and some statistical attacks exploit the secret leakage and broken the early proposals. And in 2008, and Gentry, Packard, and Vakutanathan proposed a provably secure hash and Psi framework, in which the signature follows some Gaussian distribution independent of the secret key. And such a zero knowledge property gives security proof immediately. And later, some extended work claim that the Gaussian distribution is not necessary. The signature can be some distribution following the distribution independent of the public key. That is sufficient for security proof. And currently, there are two main families of GPV instantiations. The first one, I call it compact trapdoor-based family. And the representative algorithm include the Falcon and the square root just presented before. And in those signatures, the trapdoor is a full basis of the underlying lattice. And they use a well-designed basis to achieve nearly optimal quality, and then to minimize the signature size and achieve a very good performance. And the second family is the gauge-based, gauge trapdoor-based GPV. And in these families, the trapdoor is not a full basis of the underlying lattice. It becomes a hidden linear relation between the public key and the public gauge matrix. And these two families has their own advantage and disadvantage. For the first family, it allows very good performance, but to generate such a nearly optimal basis, a compact trapdoor, it is complicated, and also maybe the compact lattice trapdoor structure would also limit some extended use. And the second and for the gauge trapdoor families, the size is much larger than the compact trapdoor, but it allows a simpler key generation and signing. And another feature is it is convenient to extend the applications. And HuFu follows the gauge framework and uses the current compact gauge technique to minimize the overall size. And in HuFu, the trapdoor is actually a pair of matrices consisting of small coefficients that follows the LW error distribution. And the public key consists of two matrices A and B. The A is a uniformly random matrix over ZQ, and B is the gauge matrix PI minus the LW sample generated by A, S, and E. And under the LW assumptions, the public matrix A can be seen as a random Hermite in a random Hermite normal form, and the secret trapdoor T gives a linear relation AT equals PI. And to sign message, HuFu signing procedures can be done in two phases. In the offline phase, it first generates a perturbation vector following some discrete Gaussians of covariance S squared minus T transpose. And in the online phase, it will compute a pair of short vector Z and E such that P times Z equals E equals the hashed message minus shift centers, and the output signature would be S equals TZ plus P. And it is easy to verify that AS plus E equals the hashed message M modulo Q. And for the security proof, and the security proof is based on the fact that the whole signing procedure is simulatable without knowing the trapdoor itself. And the foundry security is based on the six assumptions. And we propose three parameter sets for NIST security level 1, 3, and 5. And as shown in the table, the public key size is fairly large. It's more than several thousands kilobytes. But its signature size is comparable to deletions, but it's still much larger than squirrels. And we give two version of implementations for HuFu. And as we can see, the overall performance is not very sufficient, not very efficient, but the online operation is very fast because we could launch the expensive operations in the offline phase. And then I would like to thank the Maku. Maku reported two security flaws on HuFu last month. He gives two attacks. The first one is that one can generate a new signatures for the same message by flipping some bits in the HuFu signatures. And the second attack is one can modify the length fields in the HuFu signature to trigger buffer overflows attack. And these two types attacks actually exploit the same fact that there can be multiple encodings for the same signatures. And to fix these two flaws, and we propose some countermeasures recently. And we introduce we fix the initial state for encoding and add some checking in decoding phase to defeat the bit flipping attacks, and to defeat the length modification attacks. And we just directly remove the length fields and make the signature in a fixed length by padding. And that is resembled to the ISO standards. And both two countermeasures come with very small efficiency loss. And at the last, I would like to say HuFu is currently in a very infancy, and there is some room to improve its performance. For example, recently we have seen some new gauge constructions and new techniques for trapdoor generations. by integrating these techniques, we can improve the overall size of HuFu. And the second point maybe we need to take into account is the buffer transformation. Buffer transformation would give additional security properties to signatures. However, the buffer transformation is direct, but applying it to HuFu is expensive because of the large public key size. And the question is, can we design a lightweight buffer transformation? And this is future work we would working on. And at the last, I would say the current HuFu parameters fully avoids the small modular sys attack by Leoduca, Tomaples, and Eamon. And this gives highest level security insurance. But we noticed that if we just relax the L2 norm restriction while adding some restriction on the infinite norm, and maybe we could reduce the overall size. But the question is how much we can go. It would need to quantitative investigation. Okay, that is my talk. Thanks.